First of all, it's Sunday morning, so I think we should all stand up and just... Up again, up again. Okay, so the reason I asked everybody to stand is I thought anybody in the back half of the room can come and occupy the seats. Once you're standing, it's easy for you to come forward, so... Come on, guys. Forward to come. All right. So the question was asked, who here had come across Kaggle before, and it seems like there was quite a few hands. Just to show of hands who's put in a submission to a Kaggle competition. All right, a decent number. So I'm going to do a couple of things today. For those of you who haven't, I'm going to introduce you relatively quickly to Kaggle and what we do, what we're known for. Then I'm going to talk a little bit about some of the techniques that we see. Really, the winning techniques typically divide into two different categories, and I'm going to go through those two categories. And then I'm going to end off and just show you a little bit of where we're taking Kaggle and some of the things we're working on. I'm going to aim to talk for only about 20 minutes, so think about questions, because we have a really interesting vantage point on what's happening in machine learning. So rather than me sort of guess what you're interested in hearing, I'd encourage you to think of questions, think of things you want to know, and I'll leave plenty of time for questions at the end. So I'm actually going to stand over here so I can point to my slides. So Kaggle runs machine learning competitions. Companies come to us, they put their problems up on our website, and we have a community of about 400,000 data scientists who will compete in these competitions. And so you can see that the range of problems really vary. So it could be GE wanting to take where a plane is in the air and predict flight arrival time. We've done automated essay trading with the Bullet Foundation. Our first Fortune 500 customer was Allstate, predicting insurance claims, so who was going to crash their car effectively. Merck taking chemical compounds and predicting which would make the good drugs. And then quite a lot of work with CERN on things like increasing the discovery significance of the Higgs boson. So a really, really wide range of problems. They all follow the very same simple approach though. We'll take two data sets, one is a training data set, one is a test data set. People will train everybody gets access to both data sets. You'll be able to download both data sets. Calibrate your algorithm on the training data set where we give you the answers. And on the other half, we withhold the answers and people try and build an algorithm that does as accurate a job as possible of predicting the test data set. So the fun bit about this is we show people how they're doing on the live leaderboard. So you can see here that the scores, in this case it's an error rate, the lower the better. You can see that people can put in more than one entry, so you can put in up to 5 entries per day. And a typical competition will last for 2 to 3 months. Sometimes the more complex problems will lead to run a little bit longer. So the fun thing that I think is most interesting about, one of the most interesting things about competitions is really nicely represented by this chart, which I will draw out. But the idea here is that competitions turn out to be a very effective way to get to the limits of what's possible on a data set. We saw this very, very early on. Our first first US competition and our first really serious competition result was with NASA's Jet Propulsion Lab. And what they wanted to do was they wanted to take satellite images, telescope images, and basically detect algorithmically the shape of a galaxy. So figure out, for instance, if an elliptical galaxy was stretched, you'd be able to tell whether there was dark matter between the telescope and the galaxy. So this is quite a significant problem. They've been working on it for quite some time. They put it up on Kaggle, and first really strong entry was made by a glaciologist by the name of Martin O'Leary. Show of hands who've heard of a glaciologist before today? Not very many, I hadn't either. So it turns out what Martin does in his research is he takes satellite images and detects algorithmically where the edges of glaciers are. And that algorithm happens to be, he was doing edge detection in order to measure the ellipticity of galaxies. That's an edge detection problem as well. So it turns out the approach that Martin took was a very, very good fit for the problem that NASA had put up, and he was able to make a very quick breakthrough. He actually got featured on the White House Office of Science and Technology policy blog. What they wrote is that the world's brightest physicists have been working for decades on solving one of the great unifying problems. And less than a week, Martin O'Leary, this PhD student in glaciology, was able to outperform state-of-the-art algorithms. Now, for those who are in the time, you can see within the post they reference Einstein's theory of relativity and Newton's law of gravity. So Martin was very happy with himself. After this post went up, he got on Twitter and he says, not that I'm bragging or nothing, but the White House has just compared me to Einstein and Newton, so he was feeling very smart. But he wasn't feeling very smart for long. What happens next? Is somebody passes him. And then Martin passes them, and they pass him, and he passes them. And you can see that you keep outperforming each other until you reach this point where no one is able to do any better. You reach what we call the limit of what's possible in a data set. And all of our competitions have a chart that looks like this. It's not always the case that you reach the limit as quickly as within a week or so, but you always see the best scores flattening out. And now the interesting thing about this is invariably if Martin was working on this problem in isolation without the motivation of the leaderboard, he's very unlikely to have done nearly as well as he has done in this case. And what we typically see is when an in-house, the ways companies typically use us are they have a very valuable algorithm and they want to go from where they think they're doing a good job, but they want to see where they are relative to the frontier and get the techniques that will get them to the frontier. The other reason we get used is for problems that are really pushing the edge of what's possible with machine learning. This process is very effective for figuring out, at the end of a competition, the very best that machine learning can do, whether it be essay grading or diagnosing medical diseases, and then you can figure out whether or not that's practically useful. The other interesting thing I'll say about this is we know we've hit the frontier when we can look at the correlations between people's entries on the test data set. So we can look at the correlation between people's entries on that test data set, and when people are getting all the same things right and all the same things wrong, that's when we know we're at the front, that limit. So sometimes you get a false floor where the competition is going at a certain level, and then you don't know whether that's really the limit or whether it's not. When everybody's getting the same things right and the same things wrong, it's a real bottom. The other interesting thing about this dynamic, sort of alluded to this earlier when I said Martin wouldn't have done as well if he was competing or working on this problem in isolation. You get this effect where as soon as somebody makes a breakthrough, it catalyzes other people to make a similar breakthrough. We call it internally the Roger Bannister effect after the guy who broke the 4-minute mile. The story there was that the mile race, the world record on the mile was 4 minutes and 1 second. In 1954, Roger Bannister broke it. And then 46 days later, John Landy broke that record, and before long, everybody was running a mile in less than 4 minutes. You see the same effect here, because when you know it's possible to do a lot better, people try bigger things than they would have. When you think you're at the limit, people generally are focusing on things like hyperparameter tuning, but when somebody makes a big breakthrough, there's something bigger in the data set that you have there. So just to sort of set the scene a little bit more on Kaggle, we've run some number of hundreds, a couple of hundred of these machine learning competitions now. I gave you a sense of the breadth of the types of problems. We've got a pretty good footprint in the Fortune 500, so worked with around about 30 of the Fortune 500. And we also run competitions where professors host competitions for their students. So it works well for professors who don't have to mark exams, and it works well for students because you find with the first Kaggle class competition was run by Susan Holmes from Stanford University. She said the winner, that she runs the Stats 202 class, she said the winning team spent about 100 hours putting together their competition entry. She's never been able to get students to spend 100 hours on anything ever in her competition. So Owen Zhang is up next. As mentioned, we have this community of 400,000, ranked 1 to 400,000, based on their performances in competitions. So Owen actually has just been passed. I think Roberto is now the number 1. But just like golfers are ranked, we have our statisticians ranked from 1 to data scientists ranked from 1 to 400,000. So Owen's talk, which is up next in this room, will be very interesting. You should ask him the question, when he thinks he's going to get top spot there. Just to give you a sense for how much time people are spending on these problems, so we're averaging around about 80,000 machine learning models submitted to Kaggle competitions a month. So this is a huge amount of time that people are dedicating to these competitions. Now the question I get asked most often is what are the techniques that win? And so one very interesting vantage point we have is that as machine learning techniques are evolving, we get a very quick view as to what's working and in what ways they're evolving. So the first time that neural networks or deep learning won a Kaggle competition was actually Jeffrey Hinton and his graduate student in, I think it was in around June of 2012. They won the Merck competition on taking chemical compounds and predicting which would be good drugs. Then another of his graduate students who now works at the Google acquired company DeepMind won the second competition using neural networks. So very often we end up being a proving ground for new techniques, which gives us a very good vantage point on what's working well. So I want to start off by saying that there is one thing that all top Kagglers have in common, and that is they start off by setting up a really nice environment and a really nice development environment so that they can iterate quickly. So this is often using tools like version control and Git for being able to track the performance of different approaches, as well as having just a nice data pipeline that goes from data, the raw data to some sort of predictive model. And the other thing they all have in common as well is they're tenacious. So you get passed on the leaderboard and you won't stop until you pass them. So those are the commonalities. Aside from that, what we're starting to see is that top performers are sort of splitting into one of two camps. The first camp typically tends to win problems that have more structured data. And the first thing they will do, the cookbook they use is they'll start by visualizing the data. They'll draw histograms and parallelograms and cross plots and all the typical sort of things you do when you want to explore the features or the variables. Then they'll do their feature selection, so they'll come up with clever hypotheses around what might correlate with what. And the example I give to demonstrate the idea of feature selection is this competition we did to take from a chain of used car dealers that wanted to predict which cars sold at a second-hand auction would be good buys and which would be learners. So the first thing the person did was sort of looked at the data, looked at all the different variables. The second thing they did was came up with lots and lots of hypotheses around which cars when bought at an auction would be good buys and which ones wouldn't. They tried things like dark color cars and light color cars. They tried different grouping different models together, European cars versus Japanese cars. What they found was that car color did matter, but it mattered in that unusual color cars were more likely to be reliable than standard color cars. And so the intuition there is if you're the first buyer of an orange car, by the time it's sold at the second-hand auction, it's in good condition because you were an enthusiast and looked after the car. And the way they found that was they came up with lots and lots and lots of ideas. They were able to rigorously test the ideas that worked and dismiss the ones that didn't. And then they were able to put them into some kind of machine learning model and do parameter tuning that sort of gets them that last mile. The vast majority of the work, though, is done by the feature engineering, not by the classifier. But in order to win a Kaggle competition, there are now lots and lots of people who compete. The difference between first and 20th is often very small now. You do have to be quite proficient with parameter tuning. The algorithm, interestingly, it's a show of hands who's heard of random forest. That's the most of the room. Hands up if you've heard of XGBoost. Okay, a decent chunk. So XGBoost is the algorithm that is winning most Kaggle competitions now, and it's basically a fast implementation of gradient boosting machine. This is another case of seeing the state-of-the-art machine learning sort of unfold on Kaggle. It used to always be random forest with a little bit of gradient boosting machines. Now it's all XGBoost. Okay, so that was school number one, what we call the handcrafted features approach. The second approach involves spending just about zero time on feature engineering, none whatsoever. You might have guessed, it's basically all the time spent constructing neural networks. Now this is a relatively recent thing on Kaggle, and the kinds of problems that this approach lends itself very well to are data sets that involve images, text, speech, EEGs, anything that isn't structured data. And by structured data, I sort of think of data that you would typically look at in an Excel file. So this is a competition that I'm particularly proud of that finished relatively recently. It was taking images of the eye and diagnosing an eye disease called diabetic retinopathy. Now the bottom left image here is a very diseased eye. So the way ophthalmologists will rate eyes is if you have a healthy eye, it gets a rating of 0. If you have a very diseased eye, it'll have a rating of 4. And then there's 1, 2, 3 in between. So the training data set, the test data set was created for this competition by having 2 ophthalmologists rate each eye, and then sort of creating the average agreement between those ophthalmologists. It turns out that, so the winning solution here was a neural network, and the winning solution, the agreement rate between 2 ophthalmologists was about 85%, and the agreement rate between the winning algorithm and an ophthalmologist was about 85%. So this is an algorithm that really was able to perform pretty much as well as it could possibly perform given the strength of the training data. So the technique that won this competition was convolutional neural networks. Convolutional neural networks are a flavor of deep learning that are typically doing very, very well on image problems. And the way I talk about convolutional neural networks is they're basically very sophisticated edge detection. So you can see here, this is a pre-processed eye. So this is that eye that pre-processed. It sort of brings out the blood vessels. It's easier to see the edges. In this case, this is a very diseased eye, and again, the diabetic retinopathy is marked by some of these blemishes on the blood vessels. And you can see those blemishes are a lot easier to see in the pre-processed image or the image that has been done over by a convolutional neural network. We've also done, so the other flavor of neural networks that we've seen doing very well is an approach called recurrent neural networks, and these are very good for time series problems. This problem is taking EEG data, so I'm not going to try and pronounce it. I think it's electroencephalogram. Does that sound right? I think that's what EEG is, yeah. So they basically put them on the head, and it will measure brain signals. And this competition was to take the EEG readings and basically detect whether somebody was grasping or lifting. So the utility of this is that if you can figure out whether somebody's grasping or lifting, if they go on to use a prosthetic, prosthetic arm or a prosthetic leg, if you can start to determine the intent of somebody's movements, you could actually create a sort of fully working prosthetic. This is very, very early in that direction. It turned out that the EEG signals and recurrent networks could predict with about 98% accuracy whether or not somebody was grasping or lifting. So I'm going to pause there and then move into the next section of this, which is to show you, first of all, how you can get access to some of the techniques that people are using very successfully on Kaggle. So XGBoost and the different flavors of neural networks. We have a new tool that allows that, and then give you a little bit of a peek of how we plan to take that tool and turn it into a much more significant data science resource. So just bear with me as I switch over. All right, so for those of you who have never visited Kaggle before, you come to our website and you see all these competitions. I'm going to demonstrate this new tool that we've been creating called Scripts. And before I do that, I'll just give you a bit of a sense for what we're trying to do with Scripts. So I mentioned that 80,000 machine learning models each month are created for Kaggle competitions. The problem is they currently at the moment sit on people's laptops. Nobody else, there's all this great brain power going towards creating competitions, creating competition entries, but it's sort of lost at the end of a competition, except for the rare cases, or the handful of cases where people will post their code in our forums or sort of explain their methods on our blog. And so we're trying to capture that more systematically. So I'm going to demonstrate that to you on this competition. This is a getting started problem. It's a very simple data set. It's taking handwritten digits and trying to classify those digits into a 9, a 7, etc. It's a well-known data set. Just show of hands who's heard of the this data set before. Yeah, I figured as much. It's a pretty well-known data set and pretty well studied. So just to give you a quick glimpse as to what happens when people share code on Kaggle, or historically when people have shared code on Kaggle. We have these forums, they're incredibly active. This person has created a neural network code, so they're using a neural network on this digit recognition data. In order to get it running, you need to download their version of Python. Probably have to, so you have to download their Python code. You probably have to have the same version of Python that they're running, so 2.7 or 3.4. You have to have pandas, scikit-learn, matplotlib, numpy, and lasagna, and you may even have to have the same version of those libraries as that person had. Now, you may not be surprised to see that this person has put a lot of work into describing their algorithm, and and posting it, and there's no replies, right? It's very difficult to download it and build on top of it. So what we have done is we have launched a new tool. So you can see underneath forums, we have a menu item called scripts. And with scripts, what you can do is you can create an R, Python, or Julia. We've got an R, Python, or Julia environment. You can type your code directly into Kaggle. We also have a notebook interface. And the code will execute in Docker containers in our cloud. And so once you have, and you'll notice here that the data is automatically read in. So I can just start coding immediately. And then what we do is you can use this tool for free, and Kaggle will subsidize the compute. The one catch is that your code is shared publicly using an Apache 2 license. So it's kind of like an extension of our forums, where if you have something neat that you're proud of to show off, this is a really nice way to show it off. So I'll show you some of the things that people have done. So David Chidzicki wrote a random forest that classifies the different digits and then visualizes the proximity of the different digits to each other on an XY plane. So you can see here, the 7s are close to each other, the 9s are close to each other, the 4s are close to each other, the 4s are near the 9s, the 7s are near the 9s. So the algorithm is performing as you might expect. Now let's say for a moment I'm very frustrated. So the 7s with the dashes through them are in red, which means he's getting them wrong. You can see he's consistently getting the 7s with the dashes through them. Let's say I want to improve on his algorithm. Rather than having to download his data and replicate his environment, I just hit fork script, and I have his code, the execution environment, and the data he was working on running just like that. So you compare this with the forum post that I showed you before. This has been forked 26 times, and people have done all sorts of things on top of it. A lot of these scripts, this one not so much, but a lot of them also have discussion around them where people are asking questions. Why did you do this? How does that work? So it's really created sort of a whole nother side of Kaggle, and it's very valuable for those who are looking to get familiar with new techniques. So if you go to www.kaggle.com/scripts, you'll see all the scripts that have been written. You'll see that there's TNG who created XGBoost, which is dominating the structured data problems. He's put a whole lot of scripts for different data sets on how you use XGBoost. So this one is an R Markdown script where he steps you through both with code and with descriptions. So this is Francoise Cholet, who's written a package called Keras, which is one of the easy-to-use neural network packages. Again, he has taken some of the Kaggle data sets and demonstrates how you would use Keras using data sets that are available to everybody. The other thing that we're starting to do is we're starting to allow people, the next wave for Kaggle is we're starting to allow people to upload their own data sets. This is coming in the next month. And not necessarily have a competition associated with them, but upload their data sets and collaborate on data sets and code out in the public. So one example of a data set without a competition that we posted just to try out the community's appetite for this feature was Hillary Clinton's emails. Internally, I think somebody made the suggestion that we release the Ashley Madison data. We sort of looked into that. That turns out to be illegal, whereas this is actually illegal. So it's probably good practice to draw the line at what's legal. So you can see all the different things that people have done on top of Hillary Clinton's emails. One of the ones I like is somebody ran sentiment analysis on it. And maybe the result is a little disappointing in that she shows less anger and disgust and fear than she does trust. So it may have been a bigger headline grabber if that result had turned out differently. Anyway, I'm going to stop there, and as I said, I'm happy to take questions on either anything I've talked about or things that Kaggle might have a unique insight on that I haven't spoken about yet today. So thank you very much. So any questions? Who's going to be the brave one to ask the first question? Yep.
So if there's a place, there's a role that Kaggle can play in unsupervised or like semi-supervised type of problems.
Yeah. I'll repeat the question just for people in the back who may not have been able to hear. So Kaggle seems like a good fit for supervised problems. Is there a role that we can play in semi-supervised and unsupervised problems? We have actually run one semi-supervised problem before, and we haven't done much. We have only done unsupervised problems the only way really to do unsupervised problems is to have the objective function be the unsupervised component being an input to a supervised algorithm that you can actually score. That's really the only way we can do it. We have thought a bit about, do we branch out and try and do more with semi-supervised learning and unsupervised learning? And actually, I think another very interesting area is optimization as well. What we have found is that there's such a huge range of supervised problems that we haven't nearly tapped that out. It's so much simpler to do, and I think we'd want to have a bigger concentration there, I think, before we branched out. The one area that we are starting to think a little bit about is now that we can execute code on Kaggle with the scripts tool, we're starting to think about competitions that involve things like reinforcement learning. So reinforcement learning is still an objective. This is what DeepMind, for instance, do when they're, reinforcement learning. What you're trying to do is you're not telling the computer necessarily how to do something. You tell it you're trying to optimize the score of this Atari game, and the machine can do whatever it wants to figure out what is the way to optimize score. So that's probably, as we look at branching out beyond supervised machine learning, I think optimization and reinforcement learning are two areas I think we'd like to do more. Question?
You encourage companies to keep separate additional holdout sets separate from the test set used to generate the leaderboard?
Yeah. So the question was, do we encourage companies to keep a separate test set, separate from the one used to calculate the leaderboard? Actually, I didn't really explain this in much detail, but what we actually really do is we have two test data sets. So we show the public leaderboard during the competition, and as soon as the competition ends, we throw that test data set away and we rescore people on a second test data set, because otherwise what happens is people end up overfitting to the public leaderboard. Just as an aside, it ends up being an incredibly powerful way. We very often see people overfitting to the public leaderboard set, and then when we switch over the data sets, they'll drop from first to 100. And I tell you what, those people never, ever, ever make the mistake of overfitting again. It's a very good way. I often picture this, you're coming first, you stay up with the leaderboard, the deadline ends at midnight UTC, so that's when we switch over the leaderboard. So people are sometimes staying up late at night in order to see where did they end up winning, did they end up landing in first place, and they look at first and they're not there, and second and they're not there, and they sort of keep looking down and down and down and see themselves in 100th. And very often there's quite a number of blog posts that have been written on how I've lost 100 places in 1 second as sort of an illustration of the perils of overfitting. Yeah. But yeah, that's how we deal with it.
How would you advise budding data scientists to take advantage of that?
Yeah, so we have getting started problems that are really very simple. The simplest data. So the question was, how would we encourage new data scientists to take advantage of Kaggle? We have very simple getting started data sets. So we have one on the Titanic, so taking gender, class of ticket, etc., and predicting who survived the Titanic. It's a super, super simple problem. I mean, you can start off with an algorithm. If female, then survived. If male, then didn't survive, and you'll get 77% correct. So and you can start off with Excel. We have a tutorial on how to get started in Excel, Python, and R. And so that's a really good place to start. And we joke that those getting started competitions are sort of our gateway drug. You sort of start off with that one, and then you slowly get hooked, and before you know it, you're diagnosing diabetic retinopathy. Question back. Do we have a microphone? Yeah, Shosh, you get loud.
Historically, we've had people who consistently doing well, like Goldbloom and here. But now that so many people are taking contests, do you think that some changes?
Yeah, so the question was, historically we had the same cast of characters continually doing well, but now as Kaggle's grown, do we see that changing? It's certainly the case that whereas 3 years ago we had, say, 100 people per competition, now we have 500 to 2,000. And so at the very top, you have more of a concentration of people sort of right at that limit of what's possible. So that does mean that it's harder to win competitions today than it was historically. But we still, you know, I'd say the bigger thing, so yes, it is harder to consistently win just because getting to very first place is over second requires sort of a lot of extra parameter tuning and quite a lot of tenacity. I think the more interesting thing that is happening now is you really have the competition user base sort of splitting into two. You have the people who like spending all their time constructing neural networks, which is a very different skill set from the people who prefer, you know, coming up with hypotheses around, you know, what's in the data and sort of more intuitively building models. I think that's the more interesting split, and we don't see that many people sort of crossing that divide. We see the very strong neural network performers, and we see the very strong XGBoost handcrafted feature performance. Questions? So the question was, what is the most popular language on Kaggle, and is there a relationship between the algorithm and the problem? It used to be the case, when Kaggle first started, it was very clearly R with a little bit of MATLAB, with a bit of Python and a bit of MATLAB. That's changed a lot. We see Python sort of really starting to dominate. It's also interesting that there are a lot of new neural network libraries being created. And so historically, R's advantage was that it had a better package ecosystem. So anytime a statistician or a machine learner would write a new algorithm, they'd put an R package with it. Now we're seeing a lot of the new, with the rise of neural networks, a lot of the new neural network libraries are being created in Python before R. And so there's now you have an argument to make that the Python ecosystem is becoming richer than the R package ecosystem, and you get the advantage of a stronger, more robust programming language. The one thing that R still has over Python is ggplot2, so much better visualization libraries the visualization libraries in Python in R are better than the visualization libraries in Python, which is the dominant one there is Matplotlib. Josh, you again. Louder. Yeah. So the question was for neural networks, which packages are popular? The most popular are Theano. People like Python. People are typically using Python on Kaggle, so Theano, and then the languages, then the packages built on top of Theano, which I think are Keras, Nolan, and Lasagna seem to be the big ones. We see surprisingly quite a lot less of the libraries like Torch and Cafe. We have TensorFlow, which is the new Google library. It's too early for us to know whether we're going to see it or not, but I believe that has very nice Python binding. So based on the fact that people on Kaggle typically like Python, I think we'll probably start to see some TensorFlow. Was the question?
What are some of the scientific fields that have not yet been entered into Kaggle that you'd like to see, or we're going about to see it?
So the question is, what are the scientific fields that we haven't yet seen much of on Kaggle, and what would I like to see? I think we have seen a lot. On some level, we've seen a lot of different. We've seen obviously bioinformatics, chemical informatics, particle physics, astronomy, a lot with medical imaging, EEG. So we've seen a huge range of scientific data is often complex, and Kaggle is very well suited to scientific problems because you want to figure out where the limit is, and this is a very effective way to do it. The area that I personally, and I don't think this is going to be shared more generally, but I'm a Mad King kiteboarder, and I'd like to see more wind prediction competitions. We did one with PG&E around basically predicting very short term how the wind was going to blow, so they could, for their wind farm, so they could adjust the aperture of their turbines. So that was short range weather forecasting, which machine learning does a very good job on. The more speculative, or the bigger open question is sort of medium range and longer range. Can machine learning start to do better than some of the physics-based models? And that's an open question and one that I would love to see Kaggle tackle. Question?
Does Kaggle have any plans to open formal education modules, potentially like cerebral learning processes?
Yeah. So the question is, does Kaggle have any plans to create formal education models, things along the lines of what things like Coursera are doing? And the answer to that is no. We feel like Kaggle sort of really appeals to a learning by doing type. I think I certainly fit into that category, and so we sort of feel like we sort of have our place, which is the learning by doing, giving people projects, very, very defined projects, and being able to benchmark how they're doing versus each other. And so we've done that through the getting started problem. I think that formal education, there's a lot of people doing it very well, and I don't see, like, we will focus on things that we think we can do a better job than others, and I don't believe that we can do a better job than companies like Coursera. One of my former co-workers is building an education platform at Data Robot at the moment. I think he's a world-class educator. So there are people out there who are going to do a better job of it than we will. So we have no intention of going in that direction. Question?
Are there any aspects that would block companies or prevent companies, or reasons why more companies don't run Kaggle competitions? You said there have been a couple hundred, which is impressive, but I would think that maybe if companies were more willing, there would be thousands.
Yeah, so the question was, what are the blockers that typically prevent companies from hosting Kaggle competitions? We've done several hundred, why not several thousand? I think the biggest thing is you have to be willing to open your data up, right? And so we typically find that our problems skew towards kind of machine data, or data that, if it is PII data, it has to be heavily anonymized. So that's one reason. Secondly, I think the way to think about Kaggle is we are capability extension, not capacity extension. So we are only really a good fit for a company that already has a data science team that wants to sort of bring in new techniques and see other approaches to their problems. And so that relies on a company already having a data science team. Now, what we're finding is that data science teams are either emerging in large companies where they haven't existed before, or they're starting to grow. But even so, our target market is really limited to those who already have established teams. And so what we've found is that certainly it's much easier for us if you take a sort of random selection of Fortune 500s today versus when we started 5 years ago, you see many, many, many more companies that have data science teams. So our market is growing, but it's still, we still don't have complete saturation. We'll take one more question and then I think we're out of time. Yep.
How much work goes into pre-processing the data before you put it on the competition?
The question was how much work goes into setting up a problem before we put up a competition. It sort of really varies. Typically, we try and our core market is around problems that people have tackled before, and when we take on problems that a data science team has tackled before, you get this. It's already been set up before, and so it's just a case of fitting it into our framework. That's not always the case, though. In some cases, we really do need to put some amount of work in. We have a consulting program where we'll help people set up the problem. I would say that, when we do that, we typically try and put up as raw data as we possibly can. So we try not to, because if you remove some of the rawness of the data, you end up destroying insights from the problem. Anyway, thank you very much for coming. I'll hang around for a few minutes.